All right, so buckle up because today we're going to be diving deep into natural language processing, specifically how this model called BERT is, really pushing the boundaries of how computers can understand us, understand human language. We've got some excerpts from this fascinating textbook chapter that you shared, and it's amazing to see how far we've come from like just counting words to like actually trying to decode like their meaning, the meaning behind the words.
Yeah, it's really remarkable, and this chapter really, I think, traces that evolution in a really elegant way. The thing that always strikes me is how much it mirrors how we learn language, right? Like, we start with these basic building blocks, and then from there, we kind of uncover these deeper and deeper layers of meaning and nuance.
Okay, so like let's start right at that beginning then. How do we even begin to explain something as complex as language to a computer? It's not like they're, picking up grammar books in their downtime.
Exactly. That's the challenge, right? Like, how do you represent words in a way that a computer can actually process? Basically, how do you turn words into numbers? And the chapter starts with, these kind of fundamental techniques like tokenization, which is basically, as it sounds, just breaking down these sentences into individual units, like words.
So like taking follow the white rabbit and turning it into follow the white rabbit.
Exactly.
That seems pretty straightforward. I mean, almost too simple.
It does seem deceptively simple, but even at that stage, there are already these really important considerations. Like, think about contractions, right? Like, is that one token or is it two? What about punctuation? Do you keep it or do you toss it out? And the chapter even talks about how these seemingly small choices, really depend on like what you're trying to accomplish with your NLP model. What's the task at hand?
So there's no like one size fits all approach, which I guess makes sense. But let's say we've got our tokens figured out, right? How do you actually go from a word like rabbit to something a computer can actually work with?
Yeah, this is where we kind of enter the world of representing words as vectors. And vectors are basically just, lists of numbers. So the chapter talks about this early method called one-hot encoding. And basically what this does is it creates like a unique code for each word in your vocabulary. You can almost imagine it as like this long string of zeros and then a single one in a very specific position to represent that word.
So if rabbit is like the 500th word in our vocabulary, then its vector would have a 1 in the 500th spot and then zeros everywhere else.
Precisely. But as the chapter, very quickly points out, this approach, while intuitive, it kind of runs into some problems pretty quickly, right? Because the bigger your vocabulary gets, and think about all the words in the English language, the longer and more sparse these vectors become. You end up with these like really long strings of zeros that aren't really telling us much, so it's not exactly computationally elegant.
Yeah. Sounds like a recipe for inefficiency, for sure.
Yeah.
Is that the main downside, though? Or are there, like, other limitations with one-hot encoding?
Yeah, so the other major drawback is that it treats all words as these kind of completely independent entities, right? Like in a one-hot encoding world, king and queen are as related as like king and toaster oven, right? And,
Yeah.
We intuitively know that's not true. And it highlights the need for something a little bit more nuanced, something a little more sophisticated.
Yeah, we need a way to, like, capture those relationships between words, not just, like, their presence or absence in a text. And that's where word embeddings come in, right? These kind of give words more, I don't know, personality.
That's a great way to put it. So yeah, instead of just this binary on or off signal, word embeddings represent words in this kind of continuous vector space where their position relative to other words actually encodes semantic meaning.
Okay, this is where it starts to feel like we're, like, cracking the code of language a little bit. And the chapter mentions this model called Word2Vec, which was like a big step in this direction, right? What's the story there?
Yeah, Word2Vec was this kind of major breakthrough because it learned these embeddings by analyzing massive amounts of text and basically figuring out how words are used in context. So instead of just telling a computer that, king and queen exist, it can learn from reading tons of text that, hey, these words often appear in similar contexts. There's probably a relationship there.
So it's like Word2Vec is reading like tons of books and articles, kind of paying attention to which words tend to like hang out together, and then it uses that information to create these maps of meaning, essentially.
Precisely. And, what's remarkable is that this process leads to some pretty astonishing results. And this is where we get that famous example from the chapter, which is this equation, king man plus woman equals queen.
Wait, you can do math with words? That still blows my mind, even though I've heard about it before.
It is mind-blowing, and it really shows you that these word embeddings are capturing something very fundamental about how words relate to each other. It's not just about like surface level patterns, but these deeper semantic relationships, right? The model has essentially learned that the concept of king is to man as queen is to woman.
It's like the model is uncovering these like hidden connections within language itself. And it makes you wonder what else it might be able to teach us about how we think and communicate.
It's a powerful idea. But the chapter doesn't stop there, right? It also introduces this other kind of influential approach to word embeddings called GLOVE. And instead of focusing on like word pairs in this kind of local context, GLOVE takes this more global view. It looks at like how often words co-occur across, a massive, massive data set.
So Word2Vec is like analyzing a single conversation, while GLOVE is like studying an entire library.
Exactly. It's all about capturing these kind of broad statistical patterns in how we use language. And, both Word2Vec and GLOVE were like these huge game changers. But the chapter also kind of subtly hints at the fact that even these really sophisticated approaches have limitations.
There's always another layer, isn't there? What are we missing when we just rely on these more traditional word embeddings?
Well, the challenge is that words are inherently slippery creatures, right?
Yeah.
Like a single word can have multiple meanings depending on the context. And that's really where this next generation of models like ELMo come into play.
All right, you've officially piqued my curiosity. But before we jump into the world of contextual embeddings, let's take a quick pause and come back fresh to explore how ELMo tackled this challenge. Okay, so we've gone from like basic words to these fascinating maps of meaning, these word embeddings. But as we were saying, like context is everything. A single word can like completely shift and change its meaning just based on, the company it keeps, the other words around it.
Exactly. I mean, think about it, right? Like we do this naturally as humans. We don't just hear words in isolation. We kind of weave them into this larger understanding based on sentences, the paragraphs, the whole conversation that came before.
Yeah.
And ELMo was really an attempt to kind of give computers a little bit of that same power.
ELMo, short for embeddings from language models. Right. So what actually makes it different from like the word embedding approaches that we were talking about earlier?
Well, what's so intriguing about ELMo is that it moves beyond this idea of like a fixed embedding for each word. Instead, it generates these embeddings kind of dynamically on the fly by actually taking the surrounding words into account. It's almost as if ELMo is like reading the entire sentence and then saying, okay, in this particular context, watch must be the verb. It must be the act of observing something.
Like ELMo has this like little bit of human intuition that helps us navigate all these ambiguities of language. How does it actually achieve that, though? It's not like it's magically understanding the author's intent or something.
It's not magic, although it can sometimes feel that way. But ELMo relies on this really powerful type of neural network called a bidirectional LSTM. And essentially what this allows it to do is to look at a word in the context of both the words that came before it and the words that come after it all at the same time.
So it's not just like looking up, watch in its vocabulary of embeddings. It's actually like processing the entire flow of the sentence to figure out like, okay, what does watch actually mean in this specific instance?
Precisely. And this ability to generate these context-sensitive embeddings was a major, major leap forward. Like the chapter gives that great example of, I love that watch versus I'm going to watch that movie. ELMo can actually tell the difference, and it can even create different embeddings for other words in the sentence, like that, based on how its meaning is influenced by, watch being a noun or a verb.
It's starting to feel like we're really giving computers this like real sense of how language actually works, in the wild. But the chapter doesn't end with ELMo, does it? It kind of hints at something even more powerful. BERT. So what makes BERT such a big deal in the world of NLP?
Well, what's so fascinating here is that BERT kind of takes this concept of these contextual embeddings and supercharges it with this architecture that was already kind of revolutionizing other areas of machine learning called the transformer.
Wait, are these the same transformers that were making waves in machine translation? The ones that use this idea of attention to process these sequences of information in a more sophisticated way?
You got it. So BERT, which stands for bidirectional encoder representations from transformers, is built on this incredibly powerful transformer encoder architecture. What this means is that, instead of just looking at a word's immediate neighbors, like ELMo does, BERT can actually consider the entire sentence simultaneously. It can figure out, which words are most relevant to each other, even if they're not right next to each other.
So it's like ELMo is carefully reading a sentence like word by word, while BERT is kind of like taking it all in at a glance and instantly understanding these relationships and these nuances between even these distant words.
That's a great way to think about it. And BERT's use of this transformer architecture allows it to capture these long-range dependencies in language that were previously very, very difficult for computers to grasp. And it's one of the reasons why it's been such a game changer.
Okay, this is where things are starting to like truly feel next level. But the chapter also mentions these kind of mysterious pre-training tasks that BERT goes through, MLM and NSP. What are those all about?
Yeah, this is where we get into BERT's kind of secret sauce, this training regimen that allows it to develop such a sophisticated understanding of language. So MLM stands for Masked Language Model, and it's kind of like this giant computerized game of fill in the blank.
So BERT is given a sentence like, the quick brown jumps over the lazy dog, and it has to like figure out the missing word. It's like those vocabulary tests that we all took in school.
You're on the right track. But imagine that on a massive, massive scale, where BERT is being fed like millions of sentences where some of the words have been masked out. And it has to use the surrounding context to predict the missing words, which forces it to learn these incredibly intricate relationships between words and their meanings.
It's like giving BERT this like crash course in all the subtle ways that words, interact and influence each other. And what about NSP, next sentence prediction? What is BERT learning there?
Yeah, so NSP is all about understanding how sentences relate to each other, which, is crucial for making sense of any text that's longer than a single sentence. So in this task, BERT is given two sentences and has to figure out if they actually follow each other logically, in the original text.
So it's like BERT is learning to spot the difference between like a natural flow of ideas and just like a random jumble of sentences.
Exactly.
Which seems like a pretty essential skill for any language model that's aiming to like really understand text at a deeper level.
Yeah. Absolutely. And these two pre-training tasks, MLM and NSP, they kind of work in tandem to give BERT this remarkably nuanced understanding of language. It's almost as if it's gone through like years of language immersion, right? Where it's not just absorbing the meanings of individual words, but the way that they combine to create meaning and context.
This is all incredibly impressive. But I'm also curious about like the practical side of things, right? Like the chapter mentions this thing called word piece tokenization. How does that kind of fit into the picture, and how is it different from like the basic tokenization that we were talking about earlier?
Yeah, that's a great question. And it gets to the heart of how BERT handles this like incredible diversity and this ever-evolving nature of language. So remember how we talked about like breaking down sentences into words or like parts of words?
Right.
Well, word piece tokenization kind of takes that a step further.
So instead of just splitting walking into walk and ing, it might break it down into even like smaller chunks.
You got it.
Oh.
So it's like BERT is working with this much finer grained set of building blocks, which allows it to do some really interesting things. For example, if it encounters a completely new word, right? Like a word it's never seen before, it can actually try to make an educated guess about its meaning by analyzing those smaller word pieces.
Oh, that's incredibly clever. It's like BERT has this strategy for dealing with the unknown.
Yeah.
Which seems pretty essential given how often language, changes and evolves.
Exactly. And this is where we start to see like the true power of BERT. Because it's not just, memorizing this fixed vocabulary. It's actually learning these underlying principles of language itself, which allows it to adapt and generalize in ways that previous models just couldn't.
This is truly next level stuff. But I know BERT isn't just about, understanding language in the abstract. It's about actually putting that understanding into work, right? So what are some of the real world tasks that BERT has been used for? And how do we actually go from this like amazing language model to like actual practical applications?
Yeah, you're right. I mean, BERT's real power lies in its versatility. But before we unlock those practical applications, let's take a quick breather, and when we come back, we can explore how BERT can be fine-tuned for these specific tasks, and how tools like Hugging Face, make this cutting-edge technology accessible to a much wider audience.
Okay, so we've we've explored it, like the inner workings of BERT, this language model that can seemingly do it all, but like, how do we actually use it?
Yeah.
The chapter mentions something called Hugging Face, which sounds more like a friendly mascot than like a cutting-edge tech tool.
Yeah, it's a surprisingly apt name, actually. Hugging Face has become this incredibly a welcoming hub for anyone working in NLP, and it's made these powerful models, including BERT, far more accessible, right? Like before, you might have needed a whole team of engineers to kind of wrangle these models, but Hugging Face makes it possible for, individual developers, researchers to actually leverage them.
So it's like Hugging Face took something incredibly complex and made it like user-friendly, kind of like what WordPress did for building websites.
Yeah, that's a great analogy. And one of the things that Hugging Face excels at is this process of fine tuning, which we touched on a little bit earlier. So you can take a pre-trained BERT model, right, which already has this vast understanding of language, and then you can kind of specialize it for a very specific task.
So instead of like training a model from scratch to, say, analyze the sentiment of movie reviews, I can start with BERT, which already knows a ton about language in general, and then just kind of give it a crash course in like the nuances of movie reviews.
Exactly. Like the chapter touches on this. You're essentially, adding on this kind of little add-on to Bert's already like impressive skill set. You might feed it a bunch of movie reviews that have already been labeled, positive or negative, and it kind of learns to make those distinctions with remarkable accuracy.
It's like giving BERT this specialized vocabulary and this set of rules for this specific domain. But how like technically challenging is this fine-tuning process? The chapter mentioned this trainer class in Hugging Face. Is that kind of where the magic happens?
Yeah. And that's the beauty of it. You don't have to be like this deep learning wizard to work with these models. The trainer class kind of handles a lot of that complexity for you. You just need to provide your labeled data, choose the appropriate BERT model for the task at hand, and then, set a few parameters and Hugging Face kind of takes it from there.
So if I wanted to use BERT for a different task, like maybe building a chatbot that can answer questions about a product,
Yeah.
would the process be similar?
You'd be surprised how straightforward it is. Hugging Face offers these pre-trained BERT models that are specifically designed for things like question answering or text summarization, even translation. It's like you have this Swiss Army knife of language models all ready to be kind of customized for your particular needs.
It's incredible to think that something as complex as like understanding and responding to natural language can be broken down into these kind of manageable steps. It really speaks to like how far the field has come.
Yeah, and the applications really go way beyond just those specific tasks. Like researchers are constantly finding new and innovative ways to use BERT, right? They're
Wow.
using it to analyze like social media trends or to improve search engine results, even to aid in scientific discovery by processing vast amounts of research data.
It's clear that BERT and similar models are kind of changing the game in NLP. But with all this incredible power at our fingertips, it does make you wonder about the potential downsides, right? Like the chapter ended on this somewhat thought-provoking note, touching on the ethical implications of this technology.
Yeah, it's an important conversation to have because as these models become increasingly sophisticated, we really need to be mindful of how they're used and making sure that they're not misused, right? Like that they're not used to spread misinformation or to create harmful content. That's crucial.
It's this reminder that even with all the amazing advancements in artificial intelligence, human judgment and ethical considerations are more important than ever.
Absolutely. I think it's this shared responsibility, right, to ensure that these powerful tools are used for good, to augment human capabilities and understanding, not to diminish them.
Well, that feels like the perfect note to end our deep dive on a journey from the simplest building blocks of language to these incredibly powerful models that are changing how we interact with information and even with each other from words to wisdom indeed.